Okay, now let's continue our content for Calculus 2 class. This is where we stopped last time. So last time we talked about Taylor series. So you can see that the point about the Taylor series, you need to memorize the formula here, which is FA plus F prime A plus F prime A times X minus A, and then you keep going to the infinity order. This is a Taylor series, and last time we learned how to build a Taylor series for cosine x. You can see that when I build a Taylor series for cosine x, I differentiate and then put it here, and then I plug in at the center. Here center equal to 0, so I plug in 0 0 0 0 0 here, so I get the coefficients for each term, and then after that I get the cosine function. So this is very important in terms of, you can see that the cosine function here, we can use a Taylor series and expand it in terms of polynomials. So you can see that actually cosine x gonna be just 1 plus 1 minus 1 half times x squared, and so on. So on page number 10, here this is all the important Taylor series that you shall see that it's going to be something that it's very useful in the future, because for each function here you can construct a Taylor series that correspond to that function, and it's going to be useful later when you're trying to do something about sine, cosine, logarithm, or arctan, because you can do the Taylor series here. Okay. Alright, so now let's try to do the example about the Taylor series here. So I'll add more page here and do Taylor series. So example. Let's say, what if you want to integrate arctan x dx x from 0 to 1. If you want to integrate arctan, if you remember that from calculus 1, if you want to integrate arctan x can be done by using integration by parts. This is the correct way to do it. So you can do integrate arctan by using integration by parts. If you pick u to be arctan x and you pick dv to be the x, you use integration by parts. So you're gonna get the integration of arctan x. But this time we're gonna find this one by using the Taylor series. So let's say that we want to evaluate this one by using let's say we're gonna do Taylor polynomials of degree 5, center at 0. 5 of arctan x, center at 0. So this is the question is in red. So I want you to compute integrate arctan x dx from 0 to 1 by using the Taylor polynomial of degree 5 of arctan x center at 0. What would you do here? So you're gonna just go back to the Taylor series page on the previous page, and then you take the Taylor series for arctan x, and then you cut it at degree 5, and then you integrate it. This is the way that usually people do it in real life, so you don't have to go to use by part, the mess up with picking u and dv for integration by part. So what you can do is you go back here, and then you can see that for Taylor series arctan, you can expand a series of arctan, and then you get this one. So this is actually arctan x equal to this one. So basically it's gonna be something like we know from the previous page that if you take the arctan x and then you expand the series of arctan x, it's gonna be x minus x cubed over 3 and then plus x to the 5th power over 5 and so on, minus, keep going. So this is actually the series of arctan x. By using the Taylor series, you do the series of arctan x and then you get this one. And then if you want to integrate 0 to 1 of arctan x dx, you can just integrate the right hand side, which is easier. So integrate 0 to 1. Well, but the question say you cut at degree 5, so it means you only pick these 3 terms. So it's gonna be x minus x cubed over 3 plus x to the 5th power over 5 and then dx. You can see that this way you don't have to worry about the integration by parts. You have the right hand side, which is polynomial, and then you can integrate it. It's gonna be x squared over 2, right? And then plus or minus. So integrate is gonna be x to the 4th power and then over 3 times 4, which is 12. And then plus x to the 6th power over, you integrate x to the 5, you get x to the 6 over 6. And 6 times 5 is gonna be 30. And then you plug in at 1 and 0. So the answer is gonna be 1/2 minus 112 and then plus 130. So this is actually the approximation. So you can say this is approximation because you use the Taylor series of degree 5, Taylor polynomial of degree 5. And then you find the common denominator here. What is the common denominator here? 2, 12, and 30. So it should be 60. 60. So this is actually 30 minus 5 plus 2, right? Am I correct? Yes. And then here I get 27 over 60. Or in other words, I get 9 over 20. So basically you can say that integrate arctan x dx from 0 to 1. You approximate it by Taylor polynomial of degree 5 and the answer is 9 over 20. This way you don't have to use integration by part and it is an approximation. So if you want the approximation to be better, you can use more degree here. So if you feel like x to the 5th power is not that good, so you can keep going. You do x to the 7 over 7, you do x to the 9 over 9, and then you keep going. If you do the polynomial up to degree 9, you're gonna get more digits. I mean, like the approximation gets better each time when you add more terms here. Does it make sense? So maybe like in the midterm exam, you're gonna see the question that, okay, first of all, I'm gonna ask you to expand the Taylor series of arctan x, like part A, and then part B, you're gonna see the question, then you integrate this one, find the approximation. Something like, you can see that we have so many Taylor polynomial here. So on the exam, I can put like the question number 5 here. So first you expand the series of cosine x. So you're gonna show me how to do it by compute fx, f prime x, f double prime x, and keep going. And then you plug in at 0, 0, 0, 0, 0, and then you make the cosine Taylor series for cosine x. This is part A. And then once you get the Taylor series of cosine x part A, I'm gonna say that, okay, now you use the Taylor polynomial of cosine x up to degree 4. Up to degree 4 here. And then I ask you, what is the integrate of cosine x squared dx from 0 to 1, something like that, and then you can find it. Because let's see, if you want to integrate cosine x squared dx from 0 to 1, what would you do? So you know that, hey, everyone, cosine x, we know that it's gonna be this one. right? So it's gonna be 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus and so on. This is the Taylor series for cosine. If you want this one, you have to integrate. Be careful with this one because it is actually cosine x squared. So you have to plug in x squared here first. So once you plug in x squared, cosine x squared gonna be 1 minus x to the 4th power over 2 factorial plus x to the you have to plug in x by x squared. So this is going to be x to the 8th power. Makes sense? Because it's gonna be like x squared and then you raise to the 4th power. So it's gonna be x to the 8th power and then over 4 factorial and keep going. So if I said use the Taylor polynomial of cosine up to degree 4, so you're gonna get this term and then you just integrate here now. Gonna be approximation by 0 to 1 minus x to the 4th power over 2 plus x to the 8th power over 4 factorial 24 dx, and then you integrate that one. This is the value of cosine. Could be like on part B, but I mean you have to expand it Taylor series of cosine first, and then I will direct you that part 2 you can just use up to degree 4 to find the integration approximation. Does it make sense? Not that hard for Taylor series, but this is way people do in in the real world. If you want to integrate something, you don't have to just go to integration technique, because this one is way too hard to integrate by hand. You cannot integrate cosine x squared by using substitution or using integration by part, or even using trigonometric substitution, or the technique that you learn in Cal 1 cannot handle integrate cosine square, cosine x square. That is all about the Taylor series that you need to know how to apply it to find the integration. Okay, sounds good. All right, we're gonna move to the next section now. So the next section is power series. Our plan for this week, we trying to finish this handout, the Taylor series and power series. We have about 16 or 17 pages left, which should be good for 2 days, today and Wednesday. Okay, ready? So we're gonna learn how to find the radius and interval of convergence for the power series. So still you need to be a little bit expert on checking the convergence and divergence of the series, because it's gonna come up at the end of this question. So you cannot throw away the thing that you learned before, the P series, the thing that you still need to memorize that, hey, when n is when you see 1 over k to the p, it's gonna be divergent. When p equal to something, it's gonna be convergent when p equal to something. You cannot throw away, because we still want to use it for this topic. So first of all, let me introduce you about the power series. So the power series, this is the specific type of series in this form. If you see the series of this form, C0, C1, C2, up to Cn as a coefficient, and then each time when you do the series, so you do x minus a squared, keep going to x minus a to the n and non-stop keep going. This is actually called a power series. This is in general, which is kind of, you have seen it before, because the Taylor series is also a power series. So basically you're trying to attach x minus a with u, keep going with the power of x minus a with u. So basically if you plug in, what are we interested in here is, like, we interested in that the series that we have here, we call the power series. We want to know that when it is convergent and when it is divergent. So if you plug in x equal to something, it is going to be convergent when, and it's going to be divergent when. So let me trying to do example 7 with you here, so you can see the example of the power series here. So we're gonna plug in ck equal to 1 over k plus 1, and then we're gonna use center at 0 here. So once I plug in center at 0 here, so x minus a gonna be x minus 0. And then you can see that what I did here is just I start from x minus 0 here. 0 gonna be your center, and then your k here gonna be the running index. K start from 0 to infinity, and the coefficient here gonna be 1 over k plus 1. So this is actually the power series. So the power series here, if you expand it, it's gonna be something like when k equal to 0, so you're gonna get 1 over 0 plus 1, x minus 0 to the 0. And then you're doing it again, so it's gonna be 1 over 1 plus 1, x minus 0 to the 1. And then 1 over 1 plus 2, x minus 0 square. And then you keep going, it's gonna be 1 over 1. Oh, it is k plus 1, so it should be 2 plus 1 here. 2 plus 1, and this is should be 3 plus 1, and then x minus 0 cube, and then keep going. So you can see that what we did here, it looks confusing at first, but what we did here is just we keep x minus 0 here all the time, and then we're gonna say that the running index gonna be 0 here. Start from 0, and then 1, and then 2, and then 3. Every time you plug in k equal to 0, 1, 2, 3, you just keep going. And you know, we don't like this form a lot because it's hard to see. So we're gonna say that let's make it as a summation notation. So it's gonna be something like this. This is a summation notation for power series here. And okay, we meet the summation side here. Okay, the thing that we have here, A, it's gonna call center. Same thing with the Taylor series. This is gonna be called center, and the ck part here, this is actually the coefficients. So it's gonna take you for a while to get used to this form of the power series, but this is what we care. So we care that when you have the Taylor series here, if you plug in x, the series is going to be convergent or divergent. That is what we care. So x equal to 0 gonna be convergent, because if you plug in x equal to 0, you're gonna get 0 over k plus 1 for every term, and then when you sum it up, it's gonna be 0. So it is actually convergent. And then when you plug in x equal to 1, so it's actually 1 to the k over k plus 1, and this is summation 1 over k plus 1. K start from 0 to infinity, you shift the index one time, so you get 1 over k, and this is divergent by the p series. So it is actually interesting to see what x value gonna give you the convergent sequence, convergent series, and what x value gonna give you the divergent series. So we're gonna have so many examples for you to walk through for this section. So by the time you see more and more examples, you're gonna get more familiar with the power series. So we're gonna just start by taking a look at example, and then we're gonna come back to the theory part. Okay, so this is a theory that I'm gonna skip for a bit, and then we're gonna come back to the theory here later. But let me try to show you how to test the convergence and divergence of the power series here. So what we're gonna do is we're gonna use the ratio test. The thing that we learned before here, everyone remember the thing that we learned before in on the previous chapter, we learned this thing called ratio test. So the statement of the ratio test is that we have limit a subscript k plus 1 over a subscript k, right? This thing. And we're gonna test this one limit a subscript k over a sub k. If it is something less than 1, so we're gonna say that the series is convergent. Okay, let's do it here. Something less than 1, the series is actually convergent. Something bigger than 1, the series is divergent. Something equal to 1, we have no conclusion. This is the statement of the ratio test that we learned before. So we are going to use the ratio test here for the power series. So what we're gonna do is, for the power series you have here, summation of c k x minus a to the k. We're gonna just let a sub k to be the term in the power series here. And then after that, we're gonna use the ratio test to compute limit of ak plus 1 over ak. And then once you do it, so you're gonna compare with number 1 and the same thing as you did with the ratio test, because we trying to use the ratio test. It's gonna be less than 1 when it is less than 1, so we say that x value is convergent. When it is bigger than 1, x value is gonna those x value gonna be divergent, and when it is equal to 1, no conclusion. You have to do this case separately by using the technique that you learned before. It's gonna get better when you see example, but keep in mind that the thing that we're gonna use here, we're gonna use ratio test, and because the ratio test can be applied with the positive terms for the series with the positive terms, so we're gonna just put the absolute value here to make sure that everything is positive. Okay, so let's try to do example. So example 8, for what x value does the series x minus 3 to the k over k converge? So we want to know what x value, when you plug in, it's gonna give you the convergent series. You know, like if you plug in x equal to 3, let's think this way. If you plug in x equal to 3, so what happened? So it's gonna be summation k equal to 1 to infinity, and then 0 minus 3 to the k over k factorial. My plug in 3. So you plug in 3, so you're gonna get summation of 0 over k, right, to the k over k. This is actually 0 because 0 over something is 0. This is actually convergent. So x equal to 3 gonna give you the convergent sequence. But let's say if I plug in x equal to 6, what happened? So it's gonna be 6 minus 3 to the k over k, summation k from 1 to infinity. So I'm gonna get summation of 3 to the k over k. So I want to know that is this convergent or divergent? And if I plug in x equal to 2, so I'm gonna get 2 minus 3 to the k over k, sum k equal to 1 to infinity, sum minus 1 to the k over k. Is this convergent or divergent? So we are not going to plug in each value of x because this is way too slow. To just, if you plug in x equal to 2, to 3, to 1, to 6, you are not going to get all the cases, so it's going to be too slow. So what we're going to do here is, so this is your first example, so pay attention. We're going to let this thing to be your AK. So set this one to be AK. So you let a subscript k to be x minus 3 to the k over k. Okay, once you let this thing to be AK, so we plan to use the ratio test. So we are going to use the ratio test. So what we're going to do with the ratio test is you compute a subscript k minus 1 plus 1, and then you compute a subscript k, and then you take the absolute value because you want to make sure that it is positive. So to use the ratio test, and then you take limit k go to infinity. So you hope that once you get this thing, this quantity, if it is less than 1, the series gonna be convergent. Bigger than 1, the series gonna be divergent. So let's try to compute this one. So it's gonna be limit k go to 0. So what is a subscript k plus 1 here? So it's gonna be x minus 3 to the k plus 1 over k plus 1. Right, this is actually when you plug in a subscript k plus 1. And then when you plug in a subscript k, it's gonna be over x minus 3 to the k over k, right? But now I'm gonna flip it back. to the top part. So I'm gonna get k over x minus 3 to the k absolute value. And then now you make a cancellation. So what would you do here? So you're gonna just say that, okay, อาจารย์ครับ x minus 3 to the k plus 1 gonna cancel with this one. What you have left is you have limit absolute x minus 3, right? Because x minus 3 here, you have k plus 1 time. X minus 3 here, you have k times. And then you're going to cancel out, so you only have 1 time left. And then here you're going to have k over k plus 1. Does it make sense now? And then what is the limit here? So x minus 3 does not depend on k. You see that? This one does not depend on k. Does not depend on k. So we pull out x minus 3 here. Because it does not depend on k, so we pull out from the limit. And then this is going to be limit k over k plus 1. Oh, here because k is positive, so we can take absolute value out. And then this is going to be just 1. Right? Because we know that limit k over k plus 1, where k go to infinity is 1. Because this is just the basic one that if you want to, it is actually 1 over 1 plus 1 over k, so it's actually 1. This is actually x minus 3. So when you have this one, absolute x minus 3, and then take absolute value, so it means that by the ratio test, the series converge when absolute x minus 3 less than 1. You know that it's gonna be convergent when absolute x minus 3 less than 1 for sure. This is the result by the ratio test. And the series gonna be diverge when absolute x minus 3 bigger than 1. So this is the conclusion for the ratio test. But when x minus 3 take absolute equal to 1, ratio test has, ratio test cannot be applied. So we have to think when x minus 3, absolute x minus 3 equal to 1. We have no conclusion from the ratio test. So we have to try to find another way. That is not a ratio test to do it. So this is actually, let me trying to manipulate this one first. So you're gonna get here, this is the same thing with x minus 3 between negative 1 and 1. You're taking absolute value out. So it's gonna be this one, right? And if you add number 3 on both sides, so you're gonna get x between 4 and 2. Right? So basically, if x is in between 2 and 4, that is actually the interval of convergence. So the series gonna be convergent when x is in between 2 and 4. And then when absolute x minus 3 equal to 1, this is when absolute x minus 3 equal to 1 or x minus 3 equal to negative 1. That is when x equal to 4 or when x equal to 2. So at this 2 point, you need to check the convergence with the technique you learned from chapter 1. So any technique you can pick, any technique you want, and then once you have number 2 and 4 here, so you're gonna have once you plug in 2 and 4, and then you're gonna see that the series convergent or divergent. At the end, you're gonna know all x value that make the series convergent. So we're gonna just, I need another page now, but let you jot down first. Here. We're gonna come back to the theory part, and it's gonna make your world a lot easier when you see the theory. So keep this one up, and then this one going up, this one going up to this part. Okay, hold on. Make more space so I don't have to. Okay, now good. So we have to think when x equal to 2 and x equal to 4. What happened here? So when x equal to 2, so the series is summation 2 minus 3 to the k over k. K start from 1 to infinity. This is actually when x equal to 2. When x equal to 4, the series is summation 4 minus 3 to the k over k. When x equal to 2, you're gonna get negative 1 to the k over k. So for when x equal to 4, you're gonna get 1 to the k over k, which is actually 1 over k. Okay. And so negative 1 over k, negative 1 to the k over k, is this convergent or divergent? Do you remember? Negative 1 to the k over k, this is actually the series that is convergent by the alternating series test. But just 1 over k, this is actually the series that is divergent. This is by the p series or the harmonic series. So now with all information that you have here, you know that the series is going to be convergent when x is in between 2 and 4. And also it's going to be convergent as well when x equal to 2. So basically at 2, the series is convergent. At 4, the series is not convergent. So we can say that the interval of convergence this is actually include 2 but not 4. This is the interval of convergence. And this is actually what you are looking for the question. So you're looking for what x square u when you plug in. And then you're going to get the convergent series. So the answer is if you plug in x in between 2 and 4, include 2, not include 4, the series going to be convergent. And this thing gonna call interval of convergence. So I will let you jot down, write down in your notes for a minute. But we're gonna come back and summarize everything and gonna learn more techniques for you to memorize about this one. It's gonna be a long question, right? Because you have to do a lot of things. So when you jot down here, I'm gonna just come back to the conceptual questions. So some of you may have a question in your mind that why do we have to start from ratio test? The reason that we start from the ratio test is because x minus a to the k here gonna give you the idea that if you start from the ratio test, it's gonna be easy because you're gonna see this term and this term cancel out. So this is the theory developed from the ratio test that okay, when you see x minus center to the k, it's gonna be okay to use the ratio test because it's gonna cancel out anyway, and then you're gonna get this one. So ratio test is recommended for this one because you have x minus a to the n. And also root test gonna be recommended when you see something to the k as well. So we're gonna have something similar for root test as well, but this is going to be the ratio test part. So another observation that you can see is if you plug in the center, if you plug in number 3, you're gonna get the convergent series for sure because you're gonna get 0, right? So you're gonna plug in the center here, and then you always get the convergence sequence. So we can go back to the theory now. Go back to page 12. So the convergence of the power series gonna be only 3 cases. So case number 1, it could be the case that it is actually convergent only when x equal to a. The next part is maybe it's gonna be convergent, but it's convergent for all x. This is possible as well. Or the last one, there is a positive number r such that the series converge if x minus a absolute less than r, and diverge if x minus a greater than r. So here we go. So this is the power series. So the convergent pattern of the power series gonna be only 3 cases. Here, here, and here. You know that when x equal to a, when x equal to a, it's always convergent, right? At x equal to a here, always convergent, because if you plug in x equal to a in there, so it's gonna be 0. So it's gonna be okay. That, yeah, good. So most of the term gonna be 0 except the first term. So it's gonna be okay. So x equal to a gonna be at x equal to a, it's gonna be convergent series. But now the first case said that it could be the case that it is actually convergent here, only a. And then the second case said that it is convergent for the entire line here. And the last one, it could be the case that you have the radius r that is actually convergent within this radius r. So at this point, it's gonna be a plus r. This point, it's gonna be a minus r. So you're gonna know that it's actually convergent here, inside here. But at the boundary x equal to a minus r and a plus r, you have to test it by something else that you learned in chapter 1. So because the ratio test cannot be applied when x equal to a plus r and a minus r here, so you have to separate it and do it by yourself with something else. So we're gonna define the term interval of convergence. This is the one that gonna save all x value that the series is convergent, and the radius is the radius of convergence gonna be the number r here. So in this case, r equal to 0, because you can have like no radius here, so the series converge only when x equal to a. This case is r equal to infinity, so the radius is actually infinity. It's converge everywhere on the real line. And then the last one, you have the radius just r. This is possible as well to see the case that the series is actually convergent, and then you have the radius r here. It cannot be the case that you're gonna see convergent, divergent, convergent, divergent alternating. No, it's gonna be only these 3 cases. Okay. So we're gonna do more example, and then let me try to do the example with the ratio test first, because we're gonna save root test for Wednesday. So we're gonna do the example with the ratio test first. We did number 14 already, so we're gonna page 14 already. So we're gonna move to page 16 and 17. That not 16, 17, 17 and 18. That is our goal for today. So we're trying to do example 10 and example 11. Yeah, let's try to do maybe example 12 as well, but let's try to do example 10 first. I want you to find the radius of convergence and the interval of convergence for the series x to the k over k factorial. Okay, so let's do it. So you're gonna start from, here we go. So you let this thing to be a subscript k, and then you apply the ratio test. So it's gonna be, you have a sub k to be that one, and then you apply the ratio test. It's gonna be limit a subscript k plus 1 over a subscript k, and then you take k go to infinity. So this is actually the ratio test, and then you do limit k go to infinity. So a subscript k plus 1 gonna be x to the k plus 1 over a subscript k, k plus 1 factorial, and this one gonna be k factorial over x to the k, right? You just plug in the thing that you have with ak over there, and then now you cancel out. So you're gonna have limit x to the k, x to the k plus 1 gonna cancel out with x to the k. So you only have x, and then now you have k factorial over k plus 1 factorial, and k factorial and k plus 1 factorial gonna cancel out. So you're gonna get limit absolute x times 1 over k plus 1. Does this make sense? And then now you pull out x, so you're gonna get absolute x times limit 1 over k plus 1. What is the limit 1 over k plus 1 here, where k go to infinity? 0, right? So it's gonna be absolute x times 0, which is actually 0, right? Because x is just one number that you're trying to plug in, and absolute x times 0 is actually 0, less than 1. So this is the thing that less than 1. So what happened? So by the ratio test, the series summation a subscript k is convergent, right? Because any x value, you always get 0 here, which is less than 1. But by the ratio test say that when the ratio here that you compute between ak plus 1 and ak, you get something less than 1, the series is actually convergent. So it is actually convergent for all x, like any x value. It doesn't matter what you put x here, so you always get 0. So it's less than 1. So the ratio test gonna force you to say that this series is actually convergent. So what happened here is that, if you can follow me, you can imagine that here summation x to the k over k factorial, this is actually summation x minus 0 to the k over k factorial. Here you have center at 0, right? Here you have center at 0. So what happened here is, you actually know that when x equal to 0, this is at your center. So it's actually convergent here for sure. When x equal to 0, it's convergent for sure. But by the ratio test, you can make a conclusion that it is actually converge everywhere, not just 0 here. So this is the case that the series is actually convergent for all x. So the interval of convergence gonna be minus infinity to plus infinity. So it's gonna be everything. It's convergent for all x. And for the radius of convergence, it's gonna be just infinity, because like it's converged everywhere. So this is a case that we can see that it is possible that it's converge everywhere. So any x value that you plug in here doesn't matter. It's gonna give you a convergent sequence, a convergent series. So you can plug in 1, 2, 3, 4, 1/2, square root 5, any number here. The series is convergent anyway. Does it make sense? Two more examples. We're gonna show you how to deal with the case that you have the radius of convergence equal to 0 and also the radius of convergence equal to some number r. This is actually the convergent series here for all x. Alright, so some of you feel better already about after 2 examples, but we need to keep going. We need to keep going to see more examples to make sure that you are on track. So example 11. Can you find the radius of convergence and interval of convergence for this series? Okay. This time, this is your AK. Okay, let's keep doing it because this is the one that you're gonna see for sure on the exam, and it's actually the mandatory question for this chapter. So it's gonna be limit AK plus 1 over AK. And then by the ratio test, it's gonna be x minus 2 to the k plus 1 over k plus 1. Not square root. Okay. And then now you have square root k over x minus 2 to the k. And then now make the cancellation. So this gonna cancel with this. So you're gonna have limit k go to infinity. You have absolute x minus 2 here. You have square root k over k plus 1 here. So what is the limit here then? So you can pull out x minus 2, right? So remember, you have to keep absolute value with you, because if some of you take absolute value out, you're gonna get it wrong. Because if you don't have absolute value here, you're gonna have a problem when you find the radius of convergence later. So we're gonna just say that we pull out absolute x minus 2. Just pull out from the limit. So you're gonna get limit square root k over k plus 1. And this is actually 1, right? It is actually square root of 1, which is square root of 1, which is 1. So basically this is actually absolute x minus 2. When you have this thing equal to absolute x minus 2, so by the ratio test, the series is convergent when absolute x minus 2 less than 1. So what you know now is that the center is at 2. At 2, this is your center, right? Because this is 2. This is your center 2 here. So you know that the center is at 2. So it's gonna be convergent for sure at 2. So what happened here now is just x minus 2 less than 1. This is the same thing with x minus 2 in between negative 1 and 1. So they are the same thing with x in between 3 and 1, right? So which means the center is at 2. The radius is 1. You already extend the radius here. So you're gonna get 1 and 3. So inside here, always convergent already by the ratio test. Inside that, it's convergent already. But now, you know that the outside part, the one that I use the purple pen here, so this one is actually divergent already. So inside x value here is convergent already. The theory is gonna be like this. You have the convergent inside already, but with the radius 1. Outside radius 1, it's gonna be divergent already. and then now you're gonna just need to check at the endpoints 1 and 3 by yourself. So right now you can answer the question already that radius of convergence gonna be 1, because this is a radius just 1, radius 1 here from 2 to 3 or from 1 to 2. But the interval of convergence here, it's actually going to be 1 and 3, but you are not sure it's going to be this or this or this or this, depend on, you know, going to be soft bracket or it's going to be hard bracket, depends on at 1 and 3 you get the convergence or divergence or not. Does it make sense? So you just need to figure out at 1 and 3 by yourself. Okay, so now we're gonna just trying to see if it is this one or this one or this one or this one. So let's try to do x equal to 1 and 3 separately. So on the exam, this question is like 10 points, and then up to this you get 7 already. So another 3 points gonna be, you just check the endpoint. Okay, so let's do when x equal to 1 and then when x equal to 3, what happened here? So when x equal to 1, so the series is gonna be, so you plug in x equal to 1. So 1 minus 2 to the k over square root k. And then when x equal to 3, this is 3 minus 2 to the k over square root k. So when x equal to 1, the series is actually negative 1 to the k over square root k. And here, 1 over square root k. So when x equal to 1, it's negative 1 to the k over square root k. Convergent or divergent? It's 50-50, right? So on the exam you can say, you can guess, I mean, if you don't know, but it's 50-50, it depends on your luck now. But this is actually convergent. My technique is that if you see that it is actually negative 1 to the k over something, usually it's going to be the convergent by the alternating series test, because the alternating series test say that, I mean, if you recall from last week, we say that summation negative 1 to the k a subscript k, if you can show that the limit of ak equal to 0, and you can show that a subscript k is decreasing, so you're gonna conclude that it is actually convergent by the alternating series test, which means if you see summation negative 1 to the k, doesn't matter, it's over k square, over k cube, over k to the 1/2, over something, over k plus 1, over log k, whatever, it's gonna be convergent anyway, because you can apply the alternating series test. And then now, how about this one? This one should be p series, right? This is p series when p equal to 1/2. So convergent or divergent? P series p equal to 1/2 is actually divergent. Nah? Divergence. So it's actually include 1 but not 3. Okay, this is actually the answer. So include 1 but not 3. You imagine that I asked you to do show your work question, so you have to say here. But for Thai student, they just have the fill in the blank question. So if they get it wrong, they get 0 without any chance to get partial credit. But you still have a chance to get partial credit because you can show your work here.
Thank you.
But I mean, like for Thai student, they're gonna have fill in the blank question, and then just, you know, wrong it's wrong, 0 it's 0. But here you have better chance to get partial credit here.
So regardless of what their solution, what they're doing, even if they're a bit wrong, if the answer is wrong, so it's 100% wrong for Thai student.
Yeah, because they only check things in the box for Thai student.
What the hell?
Yeah, they just only have the chance to get 0 or 1.
So right now still fill in the box.
Well, I mean, for Thai student, they're gonna have 50%. 50% of the exam gonna be fill in the blank question, and 50% of the exam gonna be show your work part. So they have 50-50.
And then they should change 100% show the work. Fairness for student. Everyone can make a mistake.
Well, I mean, well, we have small class here, so lucky you. Okay, next one, the last one for today. So let's try to do example 12 here. And then for the... So I mean, like some of you may have a question, Ajahn, how do you know that when it is actually convergent, it's gonna be convergent here, and when it is divergent here, it cannot be convergent again. Because if you have something that is divergent here, so by the comparison test, the term that is bigger than you cannot be convergent, it's gonna be divergent. So it has to stop here. Alright, let's try to do the last one here. Determine the radius of convergence and the interval of convergence of this series. So how would you do it? So the same thing as before. Here, this is your AK. Okay, so we're gonna do limit AK plus 1 over AK. Shoop. And then once you do that, so you can see the pattern gonna be the same every question. So but this time you're gonna have K plus 1 factorial times X minus 10 to the K plus 1. This is A subscript K plus 1. A subscript K gonna be in the bottom. You don't have to flip this time because just that one. Super easy because K plus 1 and K gonna cancel. So you're gonna have limit absolute X minus 10. And then you have K plus 1 factorial over K factorial. And then now K plus 1 factorial gonna cancel out with K factorial. So you only have X minus 10. I pull out from the limit. And then I get limit just K plus 1. So now you know that the center of this power series is 10. Because this is actually the center 10. It's actually for sure gonna be convergent at 10. So what is the radius here? So you taking a look at this one and then limit K plus 1 where K go to infinity. This is actually infinity, right? So it means that no way this one gonna be less than 1, right? So it's actually, what the heck, this is like infinity here. So basically it's gonna be, this is the case that the ratio test cannot, you cannot bound this thing by 1, because if you know that this thing less than 1, it's gonna be convergent by the ratio test. But there's no way that this thing gonna be less than 1 unless you plug in the center. If you plug in the center, it's gonna clear out before the ratio test. If you plug in the center, it's gonna clear out and then you're gonna get 0 to the K already. So the only case that it is going to be convergent is actually at the center. Does it make sense? For this case, you can say that the radius of convergence is actually 0 because you cannot find any X value that gonna give the ratio test to be something below 1. So the radius of convergence is gonna be 0. And this case, the interval of convergence, that's no way that it's gonna converge like near 10, because the only chance that you're gonna get the convergent series, it's gonna be at 10. Yeah, 10 only. So you say equal to 10, just 1 point at the center. So it actually converge here. And all the value here divergent, all divergent here. So this is the only case, but this is the case that is not interesting. So you know, like every time when you can tell Thai student as well or ISE student, every time when they put this type of question on the exam, they're gonna put with the R here because you have to check endpoint as well. So it's much more interesting for this one, for you to check the endpoint. But this one is way too easy. They're not going to put the easy case on the exam.
You will put right. You will put right.
Well, I have not written the exam yet, but but you expect to see the question that you have to check the endpoints for sure, because this is actually more interesting and harder because you have to check the endpoint.
Actually expect both score and both score.
Very interesting.
Okay, so one more time. So this is, you already learned that there are 3 types of the convergence here. So it's gonna be the case that converge only at center, converge everywhere, or we have the radius r. But for the case that we have the radius r, you have to check the endpoints separately. Does it make sense? So on Wednesday, we're gonna come back with more examples, and we can use the root test as well. So if you don't like the ratio test, you can use the root test as well. So we're gonna learn what if we use the root test, because with some question you can use root test as well. So root test can be applied as well for this type of question, because the conclusion for the root test is gonna be the same. So we can use root test anyway. And then on Wednesday we're gonna check how to do it with the root test, and then also we're gonna complete this example, and then also we're gonna take a look at the how to work with the power series more, which is going to be just some small topic, and then we're done with chapter 9. Good. Alright, so that is all for today. If you have questions, let me know. But for the rest of the time, you can take a look at your exam 1 here. I mean, if you want to take a look more what you did wrong here. And then I'll see you Wednesday. Everyone, thank you for attending today.